Hi audience and student. Today is the day for the second lecture number 2 of this topic. But somehow I'd like to review 2 of previous lecture slides. So this is the first lecture slide where I made some mistake. And one audience emailed me pointing out the error. So I have a chance to fix this. So I'm very grateful to him about pointing this out. Okay. Let me start with this graph. This is the PWM waveforms of current mode control. As I said, the initial object of current mode control is to get rid of this ramp signal from this PWM process. So first consider there is no ramp. Okay, there is no ramp, and if some condition is met, the magnitude of impedance ratio of G2 divided by G1 is infinity, then output should be regulated at the desired value. Assume this is 15 and this is 5, okay? Then dual ratio should be 1/3 by the mechanism of this negative feedback. So for this, okay, and forget about this, okay? There is no ramp signal now, and this is not existing here, and only we have this inductor current waveforms. Then to make dual ratio, let me assume this is 10 and this is 5, then dual ratio should be 0.5. Then this control voltage V con prime will be here. Then makes the dual ratio of 0.5. Okay. Then our voltage will be 5. So automatically this V con prime, which is control voltage without employing the external lamp, then it will be here to make this dual ratio as 0.5. So in the beginning of the switching period, switch is turned on. At this moment, switch is turned off to make dual ratio of 0.5 to regulate our voltage at 5 volt as desired. Okay, this is okay if dual ratio is smaller than 0.5. But we know if the dual ratio exceeds 0.5, there is a problem, and the problem was this subharmonic oscillation. To avoid this, we need to add this ramp signal here. Okay, so now we added ramp signal. So this red body, this horizontal line is control voltage, which is different from this one. So this is V con prime, and this is a case with no V ramp or 0 V ramp. This one, so ramp signal is here, is 0. There is no ramp signal. Ramp signal is not employed. Now this ramp signal is employed here. Okay. Then I draw the ramp signal here. Okay, to make everything easier. Then this plus this is this one. So this is the current waveforms and this external lamp. Then this much is added to here, and this much is added to here. Then this V con prime will goes up like this. Why is that? What is the reason for this? That is the magic of negative feedback. So this voltage should be the 0.5. Then if this thing is raising up, then this control voltage V con prime will go up 2 bit at this point. Then dual ratio becomes 0.5, and our voltage is regulated at 5 volt. Okay, so this is the original intention of this graph. But in the previous lecture, I used some strange notation here. So this is very confusing. Okay, so delete this. This is the correct notation, correct label for this. This is the case with no ramp. Ramp signal remains 0. There is no ramp signal. You have this kind of waveforms, and the dual ratio at that case is 0.5. Our voltage is 5 volt if this is 10 volt. Okay. Now we added this ramp, then everything will go up. Okay, because you are adding this current waveform, and the ramp signal. So we have this. Then this control voltage should be raised automatically. Okay, because of these characteristics, then our voltage will be 5 volt. Okay, as desired. Okay, so this was my mistake. Okay, and I have one additional comment here. This one. Okay, this is page 10 prime. I have page 10. Okay, and I need another page here. So it is 10 prime. 10 prime. This is the condition to avoid the subharmonic oscillation without external lamp. Okay, so with external lamp to avoid subharmonic oscillation with the duty ratio larger than 0.5, you should add external lamp slope which is larger than this. Okay, so this is the minimum limit. So minimum limit is determined by this equation. This simple geometric construction will provide this formula. So this is the minimum value of slope for the external lamp. Then what is the maximum value? Okay. Maybe the maximum value will be set by the hardware constraint. Okay. If you use the PWMIs, the bias voltage is fixed, and this voltage cannot exceed the slope times the switching period is maximum Vm. Okay, suppose you have this kind of ramp. Okay, this is slope, and this is Vm, and this is Ts, period Ts. Okay, so SE should be smaller than some value which produce the time this times this is the Vm. So maximum Vm can be set probably 5 volt to 7 volt by hardware constraint. Then you cannot apply this. Okay, you cannot apply the external lamp whose slope is larger than this, right? Or you need some RC circuit here, then maybe the value of the R, value of the C, okay? Or this TS. If TS is very small, okay, then this slope can be limited by that requirement. So this upper limit will be set by hardware constraint, okay? Suppose you have this low limit and there is some hardware induced upper limit, then what is the maximum, optimum value in between? That is the question, okay? So we'll determine that later, okay? So I wrote down here, this statement is extremely important. So the ultimate goal of current mode control design is to select the optimal SE for the given condition, okay? They may apply some strange feedback, feed-forward or something digital, adaptive, optimal control, any control. There is only one available control variable. Okay, everything is fixed by power stage or current sensing network. Then only variable you can change is this SE. Right? There is only one variable you can adjust. Whatever. Any kind of control is used, eventually you have only one variable can be adjusted. Okay. To be frank with you, if you have some machine and machine will generate the different slope of this, then you adjust the machine to select the SE that provide the optimal closed performance, time domain performance or frequency domain performance. That is the optimal design. Okay. So eventual goal or eventual result of the design is to select the best possible SE. Okay, that is the only one available options for you. All right. So this is a very simple problem. Which value of SE is the optimal value? Okay, so you are looking for that optimal value, right? Okay, just keep this in mind. Okay, maybe it looks complicated or difficult, Our final goal is to find out the optimal value of this slope of external lamp. That is the only target here. Okay, that is very helpful. All right. Okay. Okay. I come back with this lecture number 2, and the title of the lecture number 2 is peak current mode control. So we went through the evolution of current mode control, and there are several different kinds of types of current mode control. Most popular one is this peak current mode control. Okay? So we'll first explain the details about this peak current mode control. Okay? And we'll investigate subharmonic oscillation, okay, by simulation without external lamp, without compensation lamp, when the Dewey ratio is larger than 0.5, and we perform the simulation at the same condition with this compensation lamp. So we'll see the stabilizing effect of this compensation lamp by simulation, time domain simulation. And this current sensing network is not easy to implement. Okay, there are many issues around about this, so I'll discuss some details about this practical current sensing network. And there are also different type of current mode control. There are many different types. Another popular one is average current mode control, and the other common scheme is charge control. They are similar. They are derived from this peak current mode control to average. So average current mode control and charge control is basically derived from this peak current mode control by modifying something, by adding some circuitry. Okay, we will be discussing that. All right. So first, let me explain the peak current mode control. So we are using the word peak here. This can mislead us. It's a misnomer, bad name for this. Okay, so many students and many people, they think the peak current mode control utilize the peak value of inductor current to control something. That is not true. Okay, so they are thinking they use the peak value of inductor current to determine the Dewey ratio, which is not true. Okay, so this is some strange name, but this is okay if you properly understand the operational principle of this. Okay, so in here, difference between this and the previous one. Previous one circle was around the inductor path. So in this figure, we assume we are sensing the inductor current, which is continuous all the time. We are assuming the CCM operation now. Okay, but here, if you take a look at this closely, this circle is here. Okay, inductor current is here, and this is what? This is switch current. Okay, so this is the switch current. So we use notation of the IQ, the switch current, and this is what? This current in this direction. Okay, no, I'm sorry. In this direction, there's diode current, ID, and this is the IL. Inductor current is IQ plus ID, okay? Or IQ is the same as IL for on time period, okay? So we are using this. Okay? You are not using this inductor current, you are using this switch current. There is a good reason for this. In the engineering sense, this is the proper place to sense the current. Okay, so this switch current is sensed by CSN and mixed with VRAM, and it fed to this negative terminal of PWM block, and using this and this QT generate the pulse width modulate the switch drive signal. So for this called switch current sensing. Okay. So this is a waveform. Okay, this is a lamp signal, compensation lamp or stabilizing lamp, and this is the this is the inductor current. So inductor current is the minimum value of inductor current, maximum value, peak value, something like this. It goes on like this. Okay, but we are sensing only this switch current. Oh, no. Inductor current is this one, not this one, this one. This is the inductor current, IL. So this lower one is IL, okay? And switch current is only this part. And we are adding this switch current to this V-ramp signal. So at this instant, this much is added to here, okay? So this is the V-ramp, okay, which is copy of this switch current, okay, with some scaling factor because of this, okay. So when this hit here, switch is turned off, okay. Suppose we sense the inductor current, okay. Then we sense inductor current, this waveform will be like this, This part is not doing anything, okay. So this is the same, okay. Even though there is an inductor current, switch is turned off at this point. Without inductor current, switch is turned off at this point. So they are the same, okay. So this is the functionally is the same in terms of the control mechanism, okay. So inductor current sensing and the switch current sensing is identical. In the dynamics, of course, the sensing method is this one is not easy, okay. Compared with this one is very easy. We'll be using this, okay. This one is not easy to sense. Because of that, they prefer to sense this. And then this inductor current sensing and switch current sensing, they are the same, okay, in terms of the control mechanism and the dynamics of this system, all right? Okay, about term peak current mode control, at this peak value of inductor current is determined by this switching from this control scheme, okay? Inductor current is not controlling, not determining the maximum value, and the control scheme determines the peak value, okay? So this peak current is not doing any. Peak current is determined by control scheme, all right? So it's not proper using this, okay? But people understand this, okay? Peak current mode control is not using peak current to turn off switch. In peak current mode control, peak value is determined when switch is turned off. Okay, they are different. You understand this, right? So current sensing is functionally identical to inductor current sensing. I explained here. Okay, and advantage of switch current sensing, and the switch current is easier than inductor current sensing. So simple current sensing network design, and if you sense this switch current sense, you are sensing the AC and the DC information. Okay, if you are sense only this inductor current, only AC information is obtained. Okay, I'm talking about the bias point. Okay, you know the variation of inductor current, but you don't know the average value of inductor current. Okay, but in this switch current sensing, you know the inductor current during the on-time period and average value of switch current. If you multiply the duty ratio or something, or divide something, duty ratio, okay, then you know the average current. Or this current can be used as to protect the switch, okay. Switch current. If switch current exceeds some value, then you shut the system to protect the switch. There is a current limit. Function is inherent with this sensing. Otherwise, you need additional circuit to sense the maximum value of your switch current. Okay, so this is the good for the overcurrent protection. For switch, this is the almost automatic, right? And another advantage of this is good news. Good news was there. What I was talking. Okay. The advantage of this. Now, for many cases, they require the output voltage of 2.1 at the current level of hundreds amps or 1,000 amps even. Okay, for that purpose, this module is used in parallel. Okay, you have a single power stage. For many cases, this module is another module here, another module here, another module here. Okay, maybe 20, 30 module is connected all together to provide the large current. Okay, but if each module is ideally identical, which is impossible, the current sharing will be different. Okay, for the 200 ampere current, this should take care of 100 amp. The other one take care of another 100 amp. Okay, but usually this guy takes 10 amp and this guy takes 190 amp. This will fail. Okay, that is called current sharing. If you have the parallel module system, you should have very good almost equal current sharing that can be implemented with this information. Okay, because we are sensing the DC and AC information of the switching current using this equal sharing among the parallel module converter will be guaranteed. Okay, right. This is an example of the subharmonic oscillation. This was buck converter, and this is input voltage, and this is the inductor current. This is the control voltage. Okay, control voltage. No. This is the control voltage here. Control voltage is fixed. Okay, and the duty ratio is increased from this value to this value. So before this value, before 0.5, maybe somewhere here, converter was stable. After duty ratio exceed this 0.5 value, it generates some. This is called the subharmonic oscillation. Okay, maybe period is a little bit different, but this can be considered as some kind of subharmonic oscillation. Okay, so this is the without compensation lamp, and I added the proper compensation lamp with the proper slope, which is the low limit. Above the low limit, which exceeds the low limit, then this subharmonic oscillation is gone. Okay, so this verifies the stabilizing effect of compensation lamp. Okay, all right. Okay, I have 4 pages about this current sensing network. So originally, I used just 1 page. That page becomes so crowded, many notations. So I split into 3 pages. Okay, this is the general diagram of general schematic, not general, exact schematic of current sensing network. And this is the switch. Okay, switch current is passing through this. This is the current transformer, which has a turns ratio of 1 to n and can be 20, 30, something like that, sufficiently larger number. And this is diode. This is a Zener diode. If you use diode here, your circuit won't work. Okay? And this is the resistance and their RF, CF. This is the noise filter. Okay? This filter out some noise. Okay? And this is this generate current feedback signal here. Okay? And then eventually that will go to the PWM block, and this part is the control waveforms. Details about this will come next slide. Okay, just understand the functional behavior of this. Okay, this is the PWM comparator, and so the switch current waveforms will appear here, and noise is removed. Okay, and through this current sensing network, and turns ratio is 1. Why you are using only 1 turn here? Because there is some resistance, the large current is passing through this. This is the main current for the output current. Okay. Then if you use larger, this is the what? Ohmic power loss will be very large. Okay. So if you use this one, the loss here will be minimized. Okay. Will be negligible. And this is necessary to reset this transformer, and this is the sensing resistance. The current waveform, something like this, will be transferred. Okay, let me sketch this. This will come later. in detail. So this looks like this. This is very similar to the switch current, but it has some noise, some additional component here. Then with this, you remove this noise component. Then the clean, this switch current waveforms will appear here. Okay, but you need generate external lamp, compensation lamp. Compensation lamp is generated like this. Okay, when this output of PWM is high, so that high voltage will be charged here very slowly. Okay, you control the time constant of this, so this is very slow. That it will grow gradually. Okay, when the PWM comparator becomes low, this is grounded. Then this charge will be discharged through this diode quickly, almost shorted. Then this will be reduced to 0. Okay, this is the external lamp, and this voltage is added. Okay, naturally, you don't need any add or something. This is a potential. This another potential. Then the result will be something like this. Okay, so this will have larger slope like this. Okay, let me move to here, and this will compared with this V cone. This is the V lamp plus VI. All right. Then what is the height of lamp? Not this one. Not this one. Okay. So there is no discharging. This will be go like this. Okay. So if you extend this slope, and this is the TS, then this peak value is magnitude of lamp, VM. Okay. You are not generating this, but you consider there is a waveforms. This will be lamp, and this is the slope of lamp. The slope will be the same. Okay. This is the functional description of this, and this is the waveform of this. Okay. So this is VI. VI is this one. Okay. And this is V lamp, and V lamp is added here. So height of this much is added here, and that is compared with this control voltage. When they meet, the switch is turned off, this voltage becomes 0, and this lamp is discharged instantaneously. Okay, but still you should consider this is extended when you are calculating VM. Okay, or you use slope here, same slope. Okay, but if you use VM to calculate the something, then you should use VM. Okay, so this is the operational waveforms of this thing. Okay, some details about this. It is not easy to understand for the first time. Okay, let's talk about this on-time period. This is on-time period. Next, we'll discuss the off-time period. Okay, so this is this circuit, current sensing network circuit employed in buck converter. This is a buck converter. There is a switch. Okay, and in the middle of this path, this current sensing network is added here, and this diode, this is capacitor, this output resistor. So this is the buck converter. It is laid down in this manner. Okay, so now everything is clear. And this is the transformer. So every transformer has magnetizing inductance. Can be large, but finite. So there is a magnetizing inductance here. Okay, and this is the LM. LM is magnetizing inductance. When switch is coming in here, okay, then the current will go out here. When this is the transformer, when current enters in the dotted terminal in the primary winding, the same current or proportional to turns ratio should go out to the secondary side, secondary circuit, come out from this dotted point. So current going into this is IQ minus IM. Okay, so this is IQ minus IM. So current here is this one. This is IQ minus IM times N. N is turns ratio. Okay, no, should be divided by n. I'm sorry. Okay. Let me put just -1 here. Or this is being mistake. Should be. It's not a voltage. It's current. This one. Okay. So this current is passing through this. Okay. This. Right. No. This. Assume this is very large. This RF and the CF is large. The current is passing through this. This current is passing through this R sense. Then this becomes the voltage Vx here. Okay. So this is Vx. This is Vx is very noisy. Okay. This noise is coming from the switching of the switch. When switch is connected, there is some spike type noise because the charge is stored in the active switch should be discharged somehow in this fashion. Okay. So noise, then noise is filtered out by this one. It's just filtering something. So you need to have some value of this corresponding to this switching frequency. Then you have these waveforms. This is this one, clean waveforms, Vx. Is Vx. Then with removing this noise component, it becomes Vi. Okay, Vi is here, and then suppose this is the high value. This is high value actually. Then this will charge this through this, and this CR is charged through this RR, and time constant is very large. So this slope is very gradual, and it reaches here, and they are added together by this simple connection. That is this one. This is Vlam plus Vi. When this hit this voltage, this becomes low. Then this will be charged. Okay, because this is ground. This diode will be conducted. Then that charge will be discharged instantaneously. Okay, that is a waveform of the current mode control here. So during this period, IM is the magnetizing current, okay, passing through this current transformer. So let me draw that. Is this one is linearly increasing. This is IM. Slope is, suppose there is some VM, okay. This is the non-linear, but somehow this can be approximate some constant. Then slope is Vm divided by Lm is the slope of Im. Okay, so this magnetizing current, right? So it increases from the zero, so it has finite magnetizing current flowing through this direction, coming out here. Okay, so this is the on-time period. So this is just half the switching waveforms up to this point. Okay, up to this point. All right. Then the remaining part of this is shown here with this red curve. Okay, IQ is 0. Okay. Okay. Here switch is closed, so IQ is this one. IQ is this one. This switch current. Okay. But here IQ is 0, so IQ is 0. So this current is coming here. Okay. So this is turned off. Then there is no path for this. Then this magnetizing current is circulating through this, and this 1 over n, not n times. This current is flowing this direction, and this Zener diode is break off. Okay, it's turned on. So Zener voltage is this direction of this polarity is reversed. This is this negative voltage. So this is this. Okay. Then Vg is reflected by this. So 1 over Vg is appearing here. Then current is decreasing, because with the negative voltage, the current is decreasing. So this magnetizing current is increased during DTS and decreased during 1 minus TS. Okay, this is the on-time period. This is the off-time period. So this performs the resetting of this current transformer. Okay, so this should be the Zener diode, not regular diode. Okay, because of this, otherwise this core will be saturated. Okay, and there is a reason using this one turn because to minimize the ohmic loss in the primary side, primary winding, through which the large main current is flowing, and this N is large because this current through this should be small. Okay, current through this should be small. Okay, right. So R sense requires some value to extract the voltage information. Okay, and this part. Okay, I forgot this. Here, this is the charging. CR, okay, and this part is all right. So this is valid for this part, this time period, and this is valid for okay. So this is for this time period, and the other one is for this time period. Okay, and I put everything together to derive the gain, current sensing network gain, and the slope of external lamp. Okay, so it is obvious switch current is passing through this, and there is a turns ratio 1 divided by n. This is the dimension is current, and the multiply this. Okay. So current sensing network gain is simply multiplication of this 1 over turns ratio and this current R sense, current sensing resistor. Okay, this is CS gain. All right, V lamp. This is the exact expression for the V lamp. Okay, so it is increasing exponentially. Okay, so it will be something like this. This final value. So it is increasing very slowly. Constant is very, very small. Okay, then can be considered this one. So for the mathematical expressions, this is the CSN gain. Ri. Ri is, you will be using this many times later. All right, so very simple. Okay, and we have this kind of approximation. This is a Taylor series expansion of something. When x is small, then this is approximation. Okay, so this is x. This is x. Okay, then this is the equation. They cancel. And this minus 1 cancel, minus cancel, and then this is the linear equation, this part. Okay, this is slope. Okay, linear slope is this value is Sn. Slope of external lamp. Okay. All right. So this is the description. DG. This Zener diode. This set the transformer. When the switch, main switch is open and the RF, CF forms the noise filter, it's not difficult to design this. You may use the try and error method to have a clean waveforms here. Okay, and the DR provide, this is necessary to provide the fast discharging, to minimize the turn-off time of this main switch. All right, this is the one example. This looks complicated, okay? And operation is not easy to understand. But once you build up this, if you implement this using some component, you can understand this. This is not difficult, okay? Very simple circuit analysis, okay? Somehow in the PWM chip, for the current mode control PWM chip, something is strange, okay? That this lamp signal generation is not clear, okay? They wrote down something, but I cannot understand. Right. So I'm using this circuit. Okay, they internally they have something, but I usually ignore the internal circuit of PWM IC, and I added this circuit externally, and this works very well. Okay. And this is another example of current mode control. Okay. Right. Let me explain this first. This is something else. Something else. This is called offline flyback converter. There is a converter called the flyback converter. Structure is shown here. Structure is shown here. It's not important, but this offline is important. Offline is, this is the AC voltage coming out of this wall outlet. Okay. So this is the AC voltage, AC 200, 60 Hertz type. Peak value is 220 times square root 2. Okay. So that we need some EMI filter. EMI filter is just to minimize some EMI noise. Okay. Just ignore this. Okay. Maybe later on you need separate study for this, but not that difficult. Okay. Control is the most difficult. Okay. Maybe the next, the magnetics will be second difficult. Okay. All right. And this rectification, then this becomes DC. Okay. If you have a resistor here, then you may see something like this, full wave rectification circuit. But with this C, there is just some DC, like some DC with some ripple component on top of that. Something like this can be considered DC. So this is a DC, and this is the DC. This is another DC to DC converter called flyback converter. And the characteristic feature of this is it has transformer in between. It provides the transfer by isolation here. Okay. So this is directly connected to the AC line. So infinity energy is coming in. So if you touch this, if there is no transformer, you will die. Okay. You will be alive, but almost you are same as the dead man. Okay. So it's better to die for that case. Okay. So, but if there is a transformer, the infinity power is coming here, but only the power allowable with this transformer will be cross this isolation boundary, so you are safe. Okay. So this for the safety purpose, all the electronics should have home electronics like the refrigerator or machine learning, washing machine, whatever, should have this type of isolation in each power supply. Okay. So this is a requirement for the safety, and this isolation is also required in this control circuit. Okay. There is a isolation here, and there should be isolation here too. Okay. With that, for that, this is the compensation circuit. Okay, using something, and this device is called optocoupler. So it contains this. This is the phototransistor and the light emit diode, infrared light emit diode in one package. So the feedback signal will be transformed to this light signal, and we will enter this. Okay, then this is the feedback. Okay, this is the feedback circuit, and the PWM modulation is performed here. And this is the current mode control. This lamp is propagated to this, and it becomes the compensation lamp. And the switch current sensing signal is this one, CSN. Okay, this is very large. The switch current, almost all of them is passing through this, and this across this resistor, that switch current will be transformed to the voltage waveform, and the PWM function is performed here. Okay. This is a very cost-effective or low-cost current mode control using this photocoupler. Okay. This is very cheap. This is control IC, and this is very cheap. This is very cheap. Okay. This is very cheap. Okay. All of them maybe cost 20 cents, like that. Very cheap. Okay. So they are using this, okay, and still they are applying the current mode control. This is what? Current sensing network. Okay. Problem of this is loss here. Okay. But they don't care loss here. Okay. This is very cheap power supply. Right. So this is the extreme example of CSN. Current sensing network gain is just RI is RSense. Okay, so this can be considered as lower end of the current sensing network, but there this is very popular for this low cost current mode control for offline flyback converter. Maybe if you go to the company making some home electronics and you are assigned the power supply division, 90%, you will be working on this converter. Okay, so this is very popular, very cheap. All right, and this is the waveforms. This is the free lamp, and VI, and this plus this generate VI plus free lamp, and it's comparing with this control voltage. The waveform is the same, but this is very cheap implementation. Okay, I'm not talking about the bad implementation. This is very, very cost-effective solution for the home electronics. Okay. All right. Okay. Okay. In the previous part of this lecture, we discussed the structure and waveform of peak current mode control, and we investigate the detailed waveforms and operation of the current sensing network. So now I'd like to explain some benefit and issues of peak current mode control. Okay. First, this is the benefit of peak current mode control. Usually, it improves dynamic performance of converter, particularly for the boost and buck boost converter, which has RHP0 in its duty ratio to output transfer function, whose load current is supported by the uptime diode code. It has RHP0, and the voltage mode control cannot be applied to those converters. Okay, but this current mode control is ideally suited for the boost and buck boost converter, which has an RHP0 in duty ratio to output transfer function. Okay, and this current mode control is good for the buck converter too. Okay, so this current mode control can be applied all the PWM converters, including the boost and the buck boost converter, of course, including the buck converter. Okay, and that is the first benefit of using current mode control. And second one is this: the converter dynamics remains the same, almost the same, regardless of the change in the CCM and the DCM operation of the operational mode of converter. Previously, we have seen that the voltage mode control is good for the buck converter when converter is in CCM mode. Okay, if converter enters into the DCM mode, the closed performance will be deteriorated. Frequency domain characteristics will be degraded, and the time domain response will be degraded either. Okay, because they are closely related. But if you use this current mode control, you can obtain the consistent performance of your converter regardless of its operational mode. That is another big advantage. And next one is design of this voltage feedback compensation becomes simpler than the case of voltage mode control. In the voltage mode control, we use the 3-pole 2-0 compensation. People usually call it type 3 compensation. I don't know why they call it type 3. Okay, but for the current mode control, you can use this 2-pole 1-0 compensation. They call it type 2. Okay, because there are 2 S's. Okay, 2 poles. Because there are 3 poles in type 3. Okay, and they have type 1 compensation, which has only integrator. Nobody will use that. Okay, so this is type 1, type 2, type 3 is some funny story. Okay, but important thing is this 2-pole 1-0 compensation can be used for all 3 basic converters, and the design process are almost the same. Okay, one single design can be adapted to all the PWM converters. Okay, and issues of current mode control. or challenges or technical barriers of current mode control. And many students and many engineers, they think current mode control is difficult, hard to understand, hard to design, hard to implement, and hard to evaluate performance of the converter. Okay, there are basically, I think there are two different reasons. One is because in the current mode control, you have the existing voltage feedback loop, and you have another loop. Okay, what you are learning in the undergrad classical control theory is a single loop control system, but this is a two-loop control system or multi-loop control system, which is more complicated and more complex to analyze and design. So that is the technical barrier, number one. Okay. So many students, they are afraid of approaching to the current mode control because of this. Okay. Another more serious problem is this current mode control has this one, sampling data feature. Okay. The PWM converter is basically sampled system because the duty ratio is only updated once in every switching period. Okay. In the exact sense, all the PWM converters are discrete time system and sampled data system, but there is a big difference between current mode control and voltage mode control. This feature, this sampled data feature, is called sampling effect of current mode control. Okay. Understanding this and incorporating this into the analysis and the design of feedback compensation is the second barrier, second technical barrier for the student and to many engineers, okay, practicing engineers. All right. I said there are big difference between voltage mode control and current mode control. There are sampling effect, okay, because the PWM converter is basically sampled data system, but in voltage mode control, this sampling effect is very weak or negligible, practically negligible, okay. The reason for that is the signal used in the PWM signal generation of voltage mode control is derived from the output voltage, which is continuous, and it is converted the V cone. Output voltage is become the control voltage V cone, which is continuous. And of course, you have this ramp signal, but this ramp is fixed. Everything is fixed. This is actually linear signal because this you have this kind of ramp signal. Here, period is fixed, known in advance, and this is fixed, slope is fixed, okay. Everything is known, so this can be considered as a constant or linear line segment or continuous signal, okay. So there is a sampling effect, but the effect is very weak and can be ignored, totally ignored in the past for the voltage mode control. But in current mode control, we are using the feedback signal from the inductor current, okay. So the control waveform is something like this for the current mode control. You have this PWM comparator here, and this the control voltage is entering here. We have external lamp, V lamp, compensation lamp. This is plus plus and this is negative. This is plus, like this. Okay? So this is a PWM block, all right? This can be considered the constant because everything is fixed. But this signal is derived from this part. This is switch current. This part is inductor current. Okay? This can be changed very rapidly. Okay? So we are using fast varying inductor current signal as a member of feedback mechanism. So in this current mode control, this sampled data feature or sampling effect is very strong, and you cannot ignore this in principle. Okay, there is the basic difference. Sometimes they ignore this, okay, but in principle, you cannot ignore this, right? So second technical barrier is the sampling effect of the current mode control, because the PWM process is derived, PWM signal is derived in the PWM block, which utilize this fast varying inductor current signal or switch signal as the component of its PWM process. So they are different. Okay. So you need address this and you need address this. Eventually, at end of this topic, you'll be knowing the all things about this one and this one almost automatically, right? So I'm teaching in that way. So you'll be overcoming this barrier number 1 and barrier number 2 gradually without realizing it. Okay? All right. Finally, I wrote down this very important statement, and this is kind of iteration of the previous statement I made in the previous lecture 1. The theme is the most important thing. The subject of current mode control design is selection of an optimal slope for the compensation ramp SE. Okay, finding out the best possible value of the SE is the theme, the only one object of this whole story. Okay, all right.